to CoffeeShop Astrophysics. We have a slightly funny speaker situation, so the best sound is going to be in these seats because we're only using one speaker. And we can click it. Great, so the UWM Planetarium has a couple more events this month, including the constellations of the zodiac Sagittarius and Capricornus, the first being later this month, and Capricornus being in December. So we are CoffeeShop Astrophysics. We are graduate students and postdocs at the Leonard E. Parker Center for Gravitation, Cosmology, and Astrophysics at the University of Wisconsin-Milwaukee. Your speakers today are myself, Ronan Humphrey. After me will be my friends Amanda Baylor and Lulu Igazu. If you have any ideas for a future CoffeeShop talk, feel free to talk to us after the presentation, or you can send us an email at coffeeshopastrophysics@gmail.com.
They're both on. There may be more interruptions like that. So today's talk is on, well, now they're both off. Now they're both off, Corey. I'll just yell. So today's talk is on JWST. Its full name is the James Webb Space Telescope. They're both on, Corey. There's nothing I can do. Oh, that's something. Okay, so we have been advised to call this telescope here JWST. Its full name is the James Webb Space Telescope, so if any of our graphics say James Webb Space Telescope or Webb, it's all the same thing. It's this big old telescope right here. So JWST is an infrared space-based telescope. It was created and run in collaboration with NASA, the European Space Agency, and the Canadian Space Agency. It was launched Christmas Day last year. We're coming up on a one-year anniversary. And it is currently orbiting the sun about 1 million miles from Earth. So its mission is fourfold. The first of its missions is to study the early universe. If you've been to one of our talks before, you've likely heard that light travels at a finite speed, which means that things are very far away, allow us to look into the past, because the light that we're seeing was sent to us very long ago. So if something is 10 light years away, we are looking at the light from 10 years ago. Similarly, we can look back even farther to 13.5 billion years ago by looking 13.5 billion light years away to the formation of the very first stars and galaxies, so the very first light in the universe. Similar to that, if we look at varying distances, we can look at how galaxies evolve over time. And this tells us about the structure of the current universe and how it got there. Thirdly, we want to study star life cycles. So what JWST is planning on doing is looking into dense gas clouds where stars are born, which will tell us about how stars are born and how they evolve over time. And lastly, other worlds. So we want to look at the atmospheres of planets, including those in our own solar system, and exoplanets, that's planets outside of our solar system. And one of the main things we're looking for is the building blocks of life, so water and carbon and things that life is made of here on Earth, which could tell us how we got here and if there's any life elsewhere in the universe. So as a bit of a refresher, if you need it, there are two main kinds of telescopes. The first is a refracting telescope. These work like a magnifying glass, or the glasses on your face, where light comes in to a big convex lens, which focuses the light down right into your eye. And then there are reflecting telescopes, which can often be larger. So these take the light into a concave mirror, point it back at a little mirror, and then bounce it into your eyes. This can be done with lots of different kinds of light. So light travels as a wave, and we categorize different kinds of light by their wavelength, which is the distance that the wave takes to get back to where it started. So from peak to peak or trough to trough. And the light that we see is all visible light. So this is only a teeny tiny part of the whole electromagnetic spectrum. And the light that JWST sees is infrared light, which has a slightly longer wavelength. So a bit of a history of telescopes in general. We'll start in 1608. A German-Dutch spectacle maker, so glasses maker, invented what he called a kieker, or what many others called a Dutch perspective glass, which is basically a refracting telescope. And a year later, Galileo Galilei, upon hearing about Dutch refracting glass, made a similar object. He called it a perspiculum, and he used this to, among other things, discover the moons of Jupiter. So while Galileo is often credited as having the first telescope, it is not strictly true, but he is the first person recorded to point a telescope at the sky for use in astronomy. So telescopes get bigger and better over the next couple hundred years, pretty much culminating in the Yerkes Observatory right here in Wisconsin. It's by Lake Geneva. And that is the largest refractor telescope, so the largest telescope with a big lens. And this is really the limit of refractor telescopes because at a certain point we can't machine the lens any bigger, and the light has a hard time getting through it because the glass that we're making is not perfectly transparent. So our modern telescopes are almost entirely reflection telescopes, such as these two here. They are the Keck Observatory telescopes. They're on Mauna Kea on the Big Island of Hawaii. They're the third and fourth largest telescopes in the world, and they each have a 10-meter diameter mirror. But at a certain point, the ground-based telescopes don't do us as good as we need them to because we have an atmosphere. The atmosphere of the Earth is really great for us because it allows us to breathe and live. However, it's difficult for astronomy because it is hazy and hard to see through. So we've moved to space-based telescopes. The first being the Orbiting Solar Observatory 1, which was launched in 1962. It is a part of 8 orbiting solar observatories that were launched between 1962 and mid-70s, all launched by NASA into low Earth orbit in order to study the sun. So this is not an exhaustive list of space-based telescopes, but another highlight, which you'll hear a lot about in this talk, is the Hubble Space Telescope. This was launched in 1990. It has a 2.4-meter diameter mirror, and it's been used to discover several things in the last 3 decades, which we'll talk a little bit about. And it's still in operation in low Earth orbit today. Next, a very different kind of light, the Chandra X-ray Observatory is also in low Earth orbit. It studies X-rays, as the name might imply, and it's sensitive to X-ray sources 100 times fainter than any other X-ray telescope up to that date. And lastly, we'll end with JWST, the topic of today's talk, which, as stated, was an infrared, or is an infrared observatory, and it has a 6.5-meter diameter mirror, so bigger than any of the others. And its mission is to improve on the discoveries of Hubble. So we should say what Hubble's discoveries are. This is also not an exhaustive list. That would be its own presentation. So one of the primary things that it's shown us is it's shown us a lot about the age and expansion of the universe. So it's able to look at very old things, tell us a little bit about how old they are, and how the shape of the universe has changed over time. It's also told us a lot about the structure of galaxies, including that galaxies have a central black hole. And it's told us about elliptical galaxies, which is a special kind of galaxy very different from our own Milky Way, which is a spiral galaxy. Third on my particular list, it's told us about our solar system, including the discovery of one of Pluto's moons, Styx, and evidence that there is a subsurface ocean on Ganymede, which is one of Jupiter's moons. Lastly, I'll end with the discovery of protoplanetary disks in the Orion Nebula, which are disks around kind of sun-like stars from which planets later form, which could tell us how we got here, how our solar system formed, and also how planets may form in other solar systems. So Hubble has left a pretty big legacy. It's one of the largest, most versatile space telescopes. It has over 15,000 papers published on Hubble data in peer-reviewed journals, so in scientific journals. And one of the ways we can tell its influence is by papers that are cited. So if a paper is really influential, other scientists will cite it a lot in their own papers. So of the 200 most cited papers, 10% use Hubble data. So there's a lot of very influential papers with Hubble data in it. And lastly, it's been an excellent tool for NASA's public engagement because it makes pictures like this. So, oh, it's back. So over the past 30 years, we've been able to see amazing pictures of space that go far beyond the void and little pinprick lights that we see in the night sky. This has really been a great tool for getting the public interested in science, making these fantastical images of amazing worlds outside of our own. So if Hubble's so great, why build JWST? Well, firstly, it's better. The mirror's bigger, it can get more light, it can see more of the sky in a shorter amount of time, and it has more sensitive instruments. Just like your phone camera gets better every year, telescope cameras get better every year. But more importantly, it's different than Hubble. So it sees in a different wavelength. It looks at infrared. Hubble sees mostly visual spectrum, a little bit of near infrared, and some ultraviolet.
And JWST sees near-infrared and mid-infrared, so it tells us different information about the universe, and Amanda's going to tell us a lot about that. So what we want to do with JWST is look at the things that Hubble found and literally look at them in a new light. Okay, so the construction of JWST was managed by the NASA Goddard Space Flight Center, and it took 30 years and $10 billion. It's quite a bit of money. It's designed to last 5.5 years, 6 months for it to get ready to do science, and then 5 years for its official science mission. But they have a goal of it lasting 10 years. So here's the parts of the telescope. It looks a little bit different than the graphic I showed of a reflector telescope, but I promise that's what it is. So the light comes in here. This big hexagonal thing, or kind of honeycomb-shaped thing, is in fact a mirror, which bounces back up to the little mirror and right into the camera. And then it has this big sun shield, which protects it from the infrared light coming off the sun, the moon, and the Earth. So it was launched from a spaceport in French Guiana on an Ariane 5 rocket. This was the main European Space Agency's help with the mission. And it had to be folded up, JWST had to be folded up to fit into the rocket. So then on its 29-day trip to its destination, it started slowly unfolding. So one of the first things to unfold was the communications antenna so that we could talk to it and it could talk to us and tell us how it's going. Then its big sun shield to protect it from the light of the sun, Earth, and the moon. Then its secondary mirror, the little one here, and then finally, and we're out. Finally, the honeycomb-shaped big giant mirror. And then it landed at its final destination here. So for a little bit of distance, this is not to scale, but the distance from the sun to the Earth is about 150 million kilometers, and then the distance from Earth to JWST is 1.5 million kilometers. And for a slight comparison, from the Earth to Hubble is only 570 kilometers, so we're a lot farther out with JWST. So why did we put it out there? The first reason being that it is a Lagrange point. So these are 5 points in space that were discovered by Joseph Louis Lagrange in the 18th century that are solutions to the three-body problem, which is you have three bodies, in our case, the sun, the Earth, and JWST, and you want them to orbit each other while staying in the same relative position. So as the Earth moves around the sun, JWST is going to stay behind the Earth. So that way its sun shield is facing both the Earth and the sun to protect it from light from both. So this is JWST's orbit. So we're looking kind of behind the Earth and behind JWST. That big diamond-shaped thing is its sun shield. That blue thing is, of course, the Earth, and there's the sun. So you can see as it goes around the sun, it stays with the sun shield facing the Earth and the sun and the moon. So once it got out to L2, oh, we're back. It spent 6 months preparing to do science. And Amanda's going to tell us about that time. Please be patient while we change buttons.
Sorry, everybody has to watch this. Oh, okay. There might be on the vision. How did you get this? Oh, I did. Okay. We're very sorry. All right. Can everybody hear me relatively well? I promise I talk really loud. Okay. Okay. So let's talk about what happens after Webb is released into space. So we have two sides. Okay. So we have two sides of the Webb telescope. We have the hot side and the cold side. And it's really, really important to keep JWST at a cold temperature, minus 370 degrees Fahrenheit, in fact. And this is because we don't want the telescope itself to radiate in the infrared. So if the telescope is too warm, its heat signature shows up on its camera, and that would just ruin the images that we want. So in order to do this, a sun shield is deployed approximately 2 weeks after the launch. In this picture, you can see the sun shield. It's the long piece that separates the hot side from the cold side. And this allows the hot side to stay from coming over to the cold side. So it's basically just a giant wall. Now, cool down also has to be carefully controlled. We can't just throw JWST out into space and say, oh, go do your thing. Because remember, we launched it from Earth. So inside the rocket ship that sent it there, it's actually full of some water particles. So once JWST unfolds into space, there's going to be water residue on it, and we don't want that to freeze immediately because space is very cold. Then that would just ruin the instruments. So there's actually heater strips placed carefully around the telescope to heat it up while it cools down, such that the cool down is very gradual and it can reach a stable temperature. So it takes several weeks to do that, but it's extremely important in the process. How do we keep it cool once it's out there? Well, I already talked about the sun shield. It's actually about as large as a tennis court, so here are some scientists for scale, but it's a very, very large sun shield. And this blocks the light from the sun, earth, and moon on one side of it from coming over to the cool side. This provides the equivalent of SPF 1 million sunscreen, so it's very, very effective. It's also composed of 5 layers, and each layer is actually as thin as human hair, so it's very, very delicate. Now you might be wondering, why is it 5 layers? Why not just one big thick layer? Well, this is actually so that each layer is successively cooler than the one below it. So in this case, since there are gaps between the layers, we can actually have heat escape out through the layers, and then it won't come up to the cool side of the instrument. Its position in orbit also aids in cooling, like Ronan talked about. The Earth, Moon, and Sun are all on the one side of the instrument, and the cool side is protected from that light and heat. So let's talk about some specs of the instrument itself. Well, it communicates to us here on Earth via high-frequency radio transmissions. So it talks to the scientists at Space Telescope Science Institute in Maryland, which you can actually go visit. That's where they communicate with the telescope. It's also solar powered, so all of the electrical components of the instrument are actually powered by the sun. There's a solar array on the bottom of the telescope here, and that takes in light from the hot side and converts it to electrical power. Not only do we need electrical power, but we also need fuel because it uses some thrusters and rockets to move it around in space and keep its position at L2. So it has enough fuel to last about 10 years, which is good because that's our scientific goal. Now, Hubble actually weighs about twice as much as JWST, despite being approximately the same size. So JWST is only about 13,500 pounds, and Hubble is 27,000 pounds. So it's pretty miraculous that they managed to get it down that far. So Ronan talked about this, but I'm going to go into more detail. What is infrared? These are wavelengths that are longer than visible light, so they can't be seen with the human eye, but they're very important for JWST. So here we have the electromagnetic spectrum, and you can see Hubble actually observes in the visible and then a little tiny bit into the near infrared zone, but it's not very good. So we have JWST, which observes from 600 nanometers to 28,500 nanometers. What is a nanometer? It's just 1 meter with 9 zeros in front of it, so it's an extremely small length measurement. And that's the wavelength it observes. So it observes in the near infrared and the mid infrared. We also have the Spitzer telescope, which observes in the far infrared, which we're not going to talk about here, but I just wanted to show it. So this also highlights the fundamental difference between Webb and Hubble, is because Hubble observes in completely different wavelengths than JWST. So why infrared? Well, it's actually really good. So it's difficult to study with ground-based telescopes because Earth's atmosphere is actually opaque to infrared. It contains water, methane, CO2, things that we can't see through with infrared light. So we have to put all of our infrared telescopes in space. Infrared also passes more easily through gas and dust in space, so anything that Hubble can't see, James Webb can essentially just see right through it. And that's illustrated here with this man with a bag on his hands. You can see in the visual picture, in the visual spectrum, you can't see through the bag. His hands are completely obscured. But if you observe him in the infrared, then you can see his hands right through the bag. This is essentially what James Webb is doing out in space. It's looking through all the stuff that Hubble can't see through. And this allows us to have high-resolution sensitivity in our images and also study objects that are too old, distant, or faint for Hubble. If you came to our talk in the spring, you'd know the universe is expanding. And when the universe expands, it takes visible wavelengths that were emitted a really, really long time ago and stretches them out into the infrared. So Webb is actually able to look much farther back because it can see those stretched wavelengths from stuff that was emitted really, really long times ago. Okay, so what actually is on JWST? There's NIRCam, which is the near infrared camera. That's this one up here. That takes pictures in the near infrared. We also have NIRSpec, which is the near infrared spectrometer. This takes spectra, which essentially tells us how light is distributed. It also tells us chemical compositions of objects as well. Then we also have MIRI, which is the mid-infrared instrument, which is pictured down here. And that allows us to observe, take pictures in the mid-infrared. And then we also have have the FGS NIRISS, which essentially, even though it's a really long name, it just keeps Webb on target. So when JWST locks onto a star that it wants to take a picture of, sometimes it has to take really, really long exposures and stay there for a really long time. In order to track whatever it wants to observe, it uses FGS to lock onto the target and stay there the whole time it's observing. We also have the spacecraft bus, which I just think is really funny, so I mentioned it here. So it's the primary support component of JWST. It's on the bottom of the instrument and essentially holds the whole thing up. It contains all the rocket thrusters, the computing power, and structural components that JWS needs to operate. Now, JWST, it's really awesome, as we've said before. However, there are a couple of problems with it. So the first one being that repairs are not currently possible just because JWST is so far away. For comparison, Hubble is only about 375 miles from Earth. So it's easy for us to go to Hubble and make repairs whenever we want to. We've actually done it a few times. But with JWST, it's 1,000,000 miles away, so it's much farther. We have no planned missions to go repair it or look at it or say hi to it or anything. It's just out there. Then we also have tears in the sun shield. Remember how I said the sun shield was as thin as human hair? It's very, very delicate. So they built it in with ripstops included to reinforce the material and keep it from ripping when it's out in space. However, in 2018, they actually accidentally ripped the sun shield while they were testing it, which further produced delays in the project. Then we also have fragile mirror segments. These are coated in glass to protect the gold. However, unexpectedly, a micrometeoroid struck one of the mirrors earlier this year in May and caused irreparable damage. So you can see, NIRCam actually took this cute little selfie right when it got out there. So this is a picture of the mirrors themselves that NIRCam has taken. And everything's fine here, there's nothing wrong here. But then they took the picture after the micrometeoroid struck, and you can see down in the bottom right corner, there's like a little white speck there. That's where the micrometeoroid struck the mirror and broke it. Now, it's actually all okay. We can still take pictures using JWST. It didn't cause such bad damage that we would notice it in any images. Okay, so let's talk about the optics a little bit. It has 18 hexagonal mirror segments, and these collectively together all make up one big giant mirror. Remember, it had to be built this way because it had to fold up and fit into the rocket ship that took it out into space. So that's why they're made from segments. Now, all the segments are covered in a gold-plated beryllium. This material reflects infrared very, very well, so that's why they made it out of this material. It's also 21 feet in diameter, so very large, and in comparison, Hubble is only about 7 feet in diameter, so it's very, very big. And then the images, you might notice, also contain these 8 characteristic spikes. Why is that? Well, I'm going to tell you. It's due to diffraction, and diffraction is the bending of light around obstacles. It can also happen based on the shape of the aperture of your telescope. So here, JWST has those 3 supports, which hold the secondary mirror out in front of the primary mirror. Now, that's really great, but they will create a diffraction pattern because the light has to bend around those struts in order to get to the primary mirror. So that creates a 6-spike diffraction pattern. Then also, we get 6 more spikes just due to the shape of the mirror because it's a hexagon. So in total, we see this 8-spike diffraction pattern. Pretty cool. Now, you can also see Hubble has its own diffraction pattern, which is only 4 spikes. Hubble has a round mirror, so the round mirror doesn't produce any extra spikes, but it is supported by 4 struts, so it has 4 diffraction spikes. This is a really great way to tell if you're looking at a Hubble image versus a JWST image, because a JWST image will always have 8 spikes, whereas a Hubble image will always have 4. This is a really great way to tell. Okay. How does it take pictures exactly? Well, it has a 3-mirror structure. So it has the giant hexagonal primary mirror, and then it also has a secondary mirror supported out in front of it. And there's actually a 3rd tiny mirror inside the telescope itself, right in this point in the center. And that reflects the light one more time right into the instrument. So this structure is actually very special to JWST. Because of the curving of the secondary and tertiary mirrors, it actually focuses the light really well and creates really, really sharp images. It prevents the light from spreading out too much, which would create blurrier images. So then this is what a JWST image looks like when it comes in, essentially. This is actually a test image taken with FGS. So this was primarily used to align the instrument and tell JWST where to go. But this is essentially what the pictures look like when they come in. It's a little oversaturated because the stars in the center appear black, but brighter spots are what's emitting stronger in infrared, and darker red spots are what's emitting less strong infrared. Now, these images, or the cameras themselves, contain filters. which emphasize different details of the objects themselves. So each of these filters is assigned to a different wavelength, and then we can assign those wavelengths to a color. And then, once we add the filters together, we can add the colors together and essentially create a composite, really pretty space image, which we'll look at later. But this also combines both art and science. So a lot of the people who actually work on the JWST images aren't scientists. Although this takes some sort of scientific understanding because we have to assign the wavelengths to colors, people who work on this are actually like graphic designers, people who just really enjoy messing around with these images. You can actually download the JWST data yourself and play around with the images and make your own at home. So I really encourage you to go do that. Okay, this is Jupiter. We've seen this before. This was taken by Hubble, and this is in the visual spectrum. So essentially, if we're right in front of Jupiter, this is probably what it would look like. It has this great red spot, which is a giant storm on Jupiter, and it's actually big enough to swallow the entire Earth. But this is what it looks like essentially through Hubble. What does this look like to JWST? Well, we have to talk about this thing called false color, because I just showed you a picture of Jupiter and it looks nothing like this. So basically, since infrared light, we can't see it with our eyes, so we have to map the infrared light to the visual spectrum, like I said, with those filters. So the longer wavelengths appear bluer, and the shorter wavelengths appear redder. So in order to do this, we have NIRCam, which took this picture in 3 filters. We have the auroras, which are reds. These are from the powerful magnetic fields that Jupiter has at its poles. And then around these magnetic fields, we have the hazes, which appear in yellow and green. But then the deeper main cloud structure is blue. And in the dark spots, which are devoid of clouds, they appear in a darker blue. And then the high altitude clouds appear in white. So the great red spot appears white because this storm is made of high altitude clouds. Now, this is really great, but you might be wondering why on Earth would we want to take this picture when we had such a nice picture of Jupiter here? And Jupiter looks nothing like this. Well, that's the point. Infrared tells us a lot about the structure of Jupiter itself. So we can look through all the gas and dust on Jupiter. We can see its magnetic fields, we can see areas that are devoid of clouds, and study the structure more carefully than we could if we just took a picture with Hubble. So now I'm going to turn it over to Lulu, who's going to talk about other worlds that JWST has taken pictures of.
Stand by for my speech. Hello? Okay. Can you hear me now? All right, awesome. All right, thank you, Amanda, for that intro. So in this next section of the talk, I'm going to be talking about several sources that have been observed with JWST and how that relates to the science goals of JWST. So first I'm going to show you something in Hubble, and then you'll see it in JWST. And we're going to start off with Neptune. Now Neptune is the farthest out planet in our solar system. Sorry, Pluto. This image of Hubble, this image taken with Hubble was taken in 2021. Neptune is a planet that has a 164-year orbit, and it's about 30 times farther away from our sun than Earth is. You notice in the Hubble picture, Neptune appears blue, and that's because of the thick methane atmosphere that Neptune has. So that any red and IR light mostly gets absorbed, and then blue light scatters. This is also kind of similar to the reason why the sky is blue on Earth. Triton, which you can see in this is not actually a Hubble image, this is just an artist's interpretation. Triton is one of the 14 moons of Neptune. It's unique in that it has a retrograde orbit. What that means is that Neptune is spinning one way, and then Triton is spinning another way. There's only a few other moons in our solar system that do that, and it's the only one of Neptune that does that. And another unique thing about Triton is that it's one of the few moons in our solar system that is geologically active. Now going back to the Hubble image, if you look right here in this corner, you can see something called the Great Dark Spot. Now originally, when scientists looked at this, they thought that this was just a hole in the atmosphere of Neptune, which is kind of right. What it really is a storm that's also about the same size as Earth. So, for example, you could fit one Earth in here. And it used to be roughly at the equator of Neptune, but it's slowly been moving up. Now there are several other storms on Neptune, but this is the only one that Hubble has been able to see. And next off, we go to the JWST image. And probably the first thing that you notice is that Triton is super duper bright. You have the classic eight spec diffraction pattern, but you also have this weird, almost diamond-like structure, and this is caused by oversaturation. What I mean by oversaturation is that there is a lot more light that JWST is getting from Triton than it is from Neptune, and this is because Triton reflects about 70% of the sun's light that hits it, whereas with Neptune, because of its thick methane atmosphere, it's actually a bit dark in the infrared. So we have to point the telescope at it for quite a while to get a good image of Neptune. But this also comes at the consequence of getting so much light from Triton that it appears super duper bright. And in addition to Triton, there's also 6 more of Neptune's 14 moons that are visible with JWST that haven't been visible with Hubble. Now if we zoom in a bit, and look specifically at Neptune, one of the first things that you'll notice is Neptune's rings. Now Neptune has 5 rings. With Hubble, only about 1 or 2 of them were ever kind of a little bit visible, but with JWST, they are super duper visible. You can see 1, 2, there's a third one here that's really faint, and then 2 more, but they're a little bit too faint to see. So the interesting thing about these rings is that they are actually significantly younger than the planet Neptune, so they didn't form when Neptune formed. The current theory is that at some point, Neptune had a 15th moon that got destroyed, and the debris from that destruction became the rings of Neptune. And then, of course, you can also see the 6 moons that were in the previous image. Another thing you can also see are these bright streaks, which are high-altitude clouds that are above the methane layer, so that they are actually visible in IR. Another thing you can see, well, it's a little bit hard on the projector, but you can see this faint equatorial band. We think this is the part of Neptune where most of its storms come from, and then its storms might move upward or downward. This little like streak all the way in the corner is the great dark spot in IR. Okay. So now let's look at a side-by-side. This is a different Hubble image of Neptune. I just chose this one because you can actually see Neptune and Triton in this image, which with Hubble you can see them, but they're just kind of dots. You can't get a lot of information about the atmospheres of either source. Whereas, of course, with JWST you can see so much more. Okay, and now in the next part, oh, that went too fast. We're going to be talking about the life cycle of stars and how we've been able to study that with JWST. Now we're going to start off with looking at the death of stars. This first source is the Southern Ring Nebula, which is a planetary nebula in the Vela constellation. Now the name planetary nebula kind of makes you think that it's related to planets. And when we first observed planetary nebula, we thought they were protoplanetary disks, which is basically a disk that forms around a brand new star where planets will eventually form. But we found out that's actually not the case. It's actually the result of a star dying. So in a planetary nebula, you have a central star. For the Southern Ring Nebula, it is a white dwarf star. And as this star was dying, it blew off tons and tons of layers of matter and gas, and that eventually formed this ring of gas and dust that you see in this image. Now, the Southern Ring Nebula happens to be a binary system, which means that there are 2 stars there orbiting each other. The white dwarf star is the source of this, of the nebula here, but this hot dying star in the middle is also in orbit, and it's also starting to die and blow off its layers, and will eventually form its own planetary nebula. And then off in this GIF here, you can kind of see a representation of what 2 stars that are in a tight orbit might look like when they're spinning around each other. And then this shell of ionized gas that is from the layers of the central white dwarf star is moving away from the nebula at about a speed of 9 miles per second. Planetary nebulae tend to only last about several thousand years. When we're talking about the life cycle of a star that might last billions of years, they're actually pretty short. So the nebula from the hot dying star will probably form sometime in the next several thousand years. Unfortunately, we won't be able to see it. now with the Southern Ring Nebula, we have two images from JWST. We have one taken with NIRCam and one taken with NIRI. The one I showed you from Neptune earlier was taken with NIRCam. In the NIRCam image, we can see the hot dying star really, really well. You can also see it in the NIRI image, and you can also see the white dwarf star. Technically, the white dwarf star is like right here in the NIRCam image, but it's almost completely obscured by the diffraction spikes, so didn't point it out there. You can also see in the NIRCam image there's a lot of this bright blue fluorescence, and that's the evidence that we have of the hot star that is in the center of the nebula that has started dying. So it started blowing off its layers and it throws off this really bright fluorescence that's super visible in IR. Another thing you can see is you can get a much better view of the gas and dust rings that are around the nebula, and they have this weird jagged pattern, which at first you would think is a little bit weird because the dust from the white dwarf would be blowing out, you would assume it would blow off in a rather spherical pattern because the star is roughly a spherical shape. But because of the motion of the orbit of the white dwarf around its companion star, it gets blown off in many, many different directions, and the NIRCam image shows gives us a very good image of that. Now over in the NIRI image, we have something relatively new discovery, which is all this red dust that is cloaking the white dwarf star. Astronomers think this is a little bit weird because the white dwarf star has already blown off all of its layers, so it should there shouldn't be any red dust covering it. It should have already been blown away, but it's still there. Might have something to do with the binary orbit. It could be from the hot dying star, but that's a little bit unlikely. Then you can see them without all the arrows. And in the background of this image that you couldn't see in the Hubble image, you can also see distant galaxies. So any of these points that are like weirdly colored, like green and yellow and orange, are probably background galaxies. The really, really bright one is probably a star. Okay, so next, we just talked about the death of stars. Let's talk about the birth of stars. The next source we're talking about is the Pillars of Creation. Now, the source of this name is pretty interesting. This was originally discovered in the 90s, but the name was taken from a sermon by Pastor Charles Spurgeon in the 1850s, where he coined the term to talk about pillars of creation being the foundation that holds up our world and everything in it. And it's kind of an apt name because, of course, the pillars, well, they look like pillars, and they also are a region of the galaxy where new stars form. There's two images from Hubble. There's one in near infrared and there's also one in visible. The near infrared image was taken in 2014, and the first visible image of the pillars was taken in 1995, but I believe this one is from about 2010. Now in the near infrared image, you can see these bright dots at the tips of the pillars, and these are newly forming stars. The way stars form in these pillars is that all of the dust and gas gets brought together under its own gravity, and it gets closer and closer and hotter until eventually it collapses on itself and forms a brand new star. Another thing you can see in the IR image is this weird, almost ethereal blue glow. And that's caused by UV light from some nearby new stars pouring down on the pillars and heating them up. So they emit in the IR. Remember from Amanda's section, whenever things are heated up, they emit IR light. And so that's why you see the IR emission, even though it's getting heated up by UV light. Now over in the visible light image, everything that you see in blue here in the background, not actually in the pillars, are from oxygen, red is sulfur, and green is nitrogen and hydrogen. Again, you can also see these star-forming regions. The pillars are almost very transparent in IR, but in visible light, you can see them a lot better. And you can also see evidence of pillar erosion from nearby young stars. So nearby young stars have really, really strong stellar wind, and that can pull away material from the pillars. Actually, some scientists that believe that the pillars have technically already been destroyed, we just haven't seen the light from it yet. For context, the pillars are about 7,000 light years away, so the light that we're seeing from them today took 7,000 years to reach us. So if in some time between then and now, the pillars were destroyed, that light hasn't had a chance to reach us yet, so we don't see it. Okay, so now with JWST, The first thing that you'll notice with especially with the near cam image, is that you can see way more background stars. In particular, when looking at the pillars of creation, any background dots that you see have to be stars because it's in a very, very thick and dusty region of our galaxy where you can't really see anything beyond it. So you couldn't see any galaxies that are super far away because there's too much stuff, because our galaxy is too thick in that particular spot. Another thing you can see is just like in the Hubble image, you can see newly forming stars. You can also see these weird, almost lava-like globules, and those are caused by new stars that are forming within the pillars. So when these new stars are forming, they're very unstable. Sometimes they release these supersonic jets, and while we can't quite see those jets because they're pretty much, they don't really emit any IR light, or at least they don't emit enough for us to see. But what you can see is how they affect the dust around it, and they kind of cause it to shoot off in different directions. You can you can see that here, and you can also see that a bit here and here. Now going over to the Miri image, one thing that you can see that you can't see in near cam is this one baby star. It is really, really bright. It happened to get captured really, really well. It's about here in the near cam image. It's still visible, but not as well. The biggest thing that you can see in the Miri image that you can't see as well in the other images is the structure of the gas within the pillars, and you can also see some of the structure of the nebula behind it. Now, the pillars of creation are part of a section of the galaxy called the Eagle Nebula. So while the pillars are a particular feature of the nebula, there's a lot more that's going on around it. So a couple things you can see is in the red are diffuse cool gas that are part of the greater Eagle Nebula. And as we go from red to dark blue, the gas is denser and denser and colder, with the densest and coolest gas at the tips of each of the pillars. Now here's a side-by-side where you can really see the difference between the gas and dust captured with the Hubble image and the JWST image. Okay. Moving on to our next scientific goal of JWST, we'll be talking about galaxy evolution. Now what we have here is an image of Stephan's quintet, which is a set of a visual galaxy cluster that is near, I think, Ursa Minor. Now this looks like it's, like all 5 of these galaxies look like they're very close together, but it's actually kind of a visual trick. The first galaxy is actually in foreground. So what that means is that it's significantly closer to us than the other 4 galaxies are. So the foreground galaxy is about 40 million light years away, whereas the background galaxies are all about 290 million light years away. So what this means is that these 4 form an actual compact galaxy cluster, and eventually, unfortunately you won't see it, but they will merge. And you can kind of see in the Hubble image, galaxies 3 and 4 look like they're very close to each other. Now in the JWST image, this is actually a composite of both NIRCam and MIRI. One thing that's really obvious is that you get much better visualization of the dust and star-forming regions of these galaxies, and you can also see direct evidence of material exchange between galaxies 2, 3, and 4. In the Hubble image, it's not quite as obvious that's happening. Okay, next we're going to be looking at the early universe. Okay, so what we're looking at here is the Hubble deep field image. This is one of the most famous images from Hubble, and how this was taken is that they pointed at a galaxy cluster that's about the size of like a grain of sand if you held it at arm's length. Well, if you pointed it at the sky, that's how big it would look like. And every single dot in here is a galaxy. If you look a little bit closely, you can see some structure of these spiral galaxies. And the way that this image was put together is they took 800 exposures, which means they pointed at the telescope at this galaxy cluster 800 times, and then stacked all that data together. If you added up all the time that the telescope was pointing at this galaxy cluster, it adds up to about 11.3 days. The closest galaxies, which are the brighter dots in this image, are roughly 1 billion light years away. That means that the light took about 1 billion years to reach us, so we're technically looking at a snapshot of these galaxies in the past. This would have been when the universe was about 13 billion years old. And the faintest dots that are almost impossible to see are from galaxies that are 13 billion light years away. This means that the light that we're looking at was from when the universe was only about 800 million years old. So again, this image tells us a lot about the history of our universe because we can take a snapshot looking back in time. Now in the JWST deep field image, this was taken with NIRCam, and this was actually taken over a much shorter time span than the Hubble image. It's only about 12.5 hours worth of data, but you still get a lot of information. You get a lot more details in the galaxies. You also get these interesting curved structures, which we call Lindsay arcs. Now this is caused by light that's traveling to us that has to travel near something that's even larger. So say we have one galaxy that's really far away, and the light from it has to travel by another galaxy that has a lot of gravity to get to us. What's going to happen is that light is going to get twisted and warped, so when we actually see it, it's going to have this weird arc-like shape. And you can see a lot of evidence of that here. You can also see a lot of sources with really, really strong diffraction spikes. This means that we are seeing them a lot brighter in JWST than we're seeing them in Hubble. And then here we have a GIF of Hubble versus JWST pointing at the same part of the sky. Now the JWST image that I showed you was pointing to a galaxy cluster in that's visible in the southern hemisphere. It's technically a different area of the sky than the original Hubble one I showed you, but there is a Hubble image that's pointing to the same area of the sky as JWST. And here you can really see the difference between JWST and Hubble. You can see that there's more galaxies visible. You can see a lot more fine structure in the galaxies that you can see. You see more evidence of gravitational lensing. And overall, you just get a lot more information out of the JWST image than you do the Hubble one. So overall, what have we learned from JWST? We've learned a lot of information about new worlds. We've learned a lot about atmospheres of planets in our solar system, but also planets outside of our solar system. We've studied the life cycles of stars. We've looked at the birth of stars. We've seen the deaths of stars. We've also looked at galaxy evolution and how star-forming regions can form between galaxies that are interacting. We can also look back in time to our early universe. Thank you for listening. Our next talk will be in December 10th, and will be about how India is space. Can take questions now if anybody has any. Yes.
So I think it was the colors that I saw online where they started comparing Hubble and Webb, and they looked so similar as far as the colorization. So I'm wondering, with Hubble being visual and the other, did they translate it before?
Yes. Whenever we take an image in IR or in infrared, it's not actually this color. We just have to translate it into a visual spectrum to get like, okay, this is a redder wavelength, and this is a shorter wavelength. So even though they kind of look like they're similar colors, they are similar wavelengths. But if we try to look at this in IR, we would see blank.
Okay, so you can approximate what the visual would be with the information.
Yeah.
We just slide it along.
Yeah. Yes.
I have a question on the resolution of the as I understand it, the wider the diameter of the telescope, the more finer the resolution.
Yes, that's correct.
But also, it's dependent on the wavelength.
Yes.
The Webb has a longer wavelength, so that would reduce it.
very
away.
far away.
Yeah, to get. So these galaxies that are out there probably look at us, I guess.
Could it be like maybe one of them is an Andromeda group, or I don't know.
The way that you could think about it is that how far away we can look is dependent on how far away something is from us. So the Milky Way is all around us right now.
Right.
So all the light takes a very short time to reach us. So if we were, say, really, really far away from the Milky Way, then the light would take longer to reach us, and then we could actually see the Milky Way in the past.
Maybe someday we can throw a telescope out there.
I'm sure there's fascinating sci-fi.
Oh yeah.
Yeah, I think we should sci-fi movies.
Yeah. Yes.
You mentioned that the mirrors are hexagonal on purpose. Can you tell me a little bit about why they picked the hexagon and not another circle?
I think it's just because of the it makes it fold, right? So
So hexagons stack perfectly. That's why bees use them in a honeycomb. So it's to make sure you don't have any gaps. In math, it's called Tyler's theorem. There's a certain number of shapes that are able to lay next to each other and fill a plane without gaps. And hexagons are one of them. So this allows us to fold it up and also have no gaps.
JWST origami, which you can download on the internet actually and fold your own JWST. I discovered that when I was doing research. Yeah. So not only can you play with the data, you can also make a little origami telescope. Keep them coming. Any other questions? Okay. You're welcome to come up and talk to us afterwards. But
Oh yeah, in the back.
So this is kind of related to what you mentioned earlier about the Milky Way. If we can't see the Milky Way, how do we know it has like the 8 arms, right? That spiral and all that.
Well, we can only look at the Milky Way kind of side on. And you see, if you go out very far into the wilderness, you can kind of see that stripe. So that's all we see. We know it's shaped the way it is because of how it moves. So we're basically guessing.